In this video, we're going to be looking at partial pressures. So a lot of the times we're going to be looking at mixtures. There's going to be more than just one type of gas in the container. Maybe they're reacting together and creating more than one product, or maybe there's some things that don't react, like if you have air, oxygen might be reacting and nitrogen gas is still in there. But either way, if we're looking at the pressure exerted by just one gas, we call it a partial pressure. So it sounds fancy, but it's really just the pressure exerted by just one component in your mixture. So if I want the partial pressure of nitrogen, you usually indicate it with a P to represent pressure. And the element or compound, whatever part that you're talking about, in this case nitrogen, you could just write the word nitrogen or N2, because don't forget nitrogen is diatomic if it's by itself. And it's just the Pivner, the ideal gas equation, but using just moles of that one component. So there's really not any new equations here. It's just if you see partial pressure, it's the pressure of just that one gas, and you're using the moles of just that one gas in Pivner. So if I'm talking about here's a mixture, let's say one of these is oxygen, one of them is nitrogen, because both of them are diatomic. Don't forget to memorize your diatomic elements. I know them as Hofbrinkel, HOFBRINCL. And if they're by themselves, they're actually diatomic. So let's say the other one's oxygen. If I wanted just the pressure of oxygen in this mixture, then I would have to count up the moles of oxygen, plug into Pivner, and I can solve for the pressure of oxygen. And it makes sense that if, let's say, these yellows are oxygen, if I have more oxygen molecules, they would be having more collisions with each other in the walls of the container, and therefore they would exert a higher pressure than the nitrogen molecules. So if you wanted to get the total pressure and you had moles of each component, you could also get the total pressure by plugging into Pivner, but with the total moles. So these are all the ideal gas equation, Pivner, but you just specify if you want the partial pressure, you use just the moles of one component. If you want the total pressure, you use the moles of all the components. And when I say components, I mean gases. You can only use Pivner with gases. So if you have a solid or a liquid, you are not plugging those moles into the total pressure. You would not be plugging in those moles to solve for a partial pressure. That substance would not be exerting a partial pressure that we are going to be calculating. If you look at this as well, I want to draw your attention to one thing. Notice in this equation, you've got moles over volume. If I rearrange Pivner to solve for just P, which is what this is, you've got moles over volume. What is moles per unit volume? What's moles per liter? Wait a minute, that's molarity. Molarity is moles per liter. So I actually could write Pivner with molarity in it. And this capital M is going to represent molarity, not molar mass. I know we have Pivner where we have a molar mass component in there. But I just want to show you that partial pressure is actually related to the molarity to the molarity of that substance. And I just down here I wrote A's to represent any compound, any element, component A. But if I look at this, so a lot of times for gases, rather than recording molarities, a lot of times people look at partial pressures for gases. And I made this note for you down here. So moles per liter is molarity. For a gas, molarity and partial pressure are directly related. If molarity goes up, concentration goes up, partial pressure goes up. So a lot of times people use molarity rather than using molarity for gases. People record partial pressures for gases, and that's really an indication of concentration. It is an indication of how many particles are packed in there per unit volume because it's proportional to that. It is directly proportional to molarity. So I just wanted to draw your attention to that. Anyway, takeaways here, partial pressures, Pivner, but with moles of that one particular substance. What's great about this, if I kind of go back here, if I were able to calculate the partial pressure of nitrogen and the partial pressure of oxygen, you should say, well, the total pressure would just be the sum of these partial pressures. And that is Dalton's law, which is actually on your formula sheet. The total pressure is the sum of the partial pressures. So some problems you might see partial pressure and total pressure, and you could subtract to find a missing partial pressure. Or you might have all the partial pressures and you can add them together to get the total pressure. So these are just some new ways that we can use Pivner or we can use partial pressures. You can either add them to get the total, or if you have the total and a partial pressure, subtract to find one that's missing. Like if you had A and B and didn't have C, you could subtract. And you can use Pivner, but with moles of just that one thing to find the partial pressure. Okay, so I want you, and this also implies that each component in the mixture behaves independently, that you don't have to rely on one to solve for the other, because you could always plug in just moles of one gas and solve for the partial pressure with Pivner. So I want you to take a moment, try this problem. Here are all different components of air, and here are their pressures in kPa, kilopascals. You don't have anything to convert here. These are actually decimal places. This is just European, so they have commas instead. I want you to take all of these components and find what would be the mixture, which would contain each of these, what would be the mixture's kPa. Take a moment. So if I have the partial pressures of each component, I can add them up to get the total. And if I add all these up, I get 101.3 kPa, which is actually standard pressure in kilopascals. I want you to take a moment and also try this slide. It says calculate the pressures of H2 and HE gases, their partial pressures in atmospheres. So here's H2 gas, I give you the moles. Here's helium gas by itself, I give you the moles. And I'm telling you all of these containers are 5 liters. They have a fixed volume. That's why you might see more weights on here to keep the volume fixed. And they all have the same temperature. And then once you do that, I want you to calculate the total pressure of the mixture, which I have represented here. It's just these two things are both now together in a mixture. Take a moment, pause the video, give that a try, and come back and check your work. So all I'm doing is I'm using Pivner. So I'm taking this moles, this liters, and this temperature, plug into Pivner, and you should get 2.9 ATM. I'm rounding to 2 sig figs here. I'm going to assume that this is 20 point with a decimal there. And this is now my moles of helium. I'm doing the same thing, but now I'm using this moles, same volume and temperature, and I should get 7.2 atmospheres. Now to get the total, I have 2 different ways I could do this from what I've learned. I could either take the 2 moles, add them together to get the total moles in my container, and then once I have the total moles in my container, I can plug into Pivner again with liters and, my volume and temperature, and I should get 10.1 atmospheres. Or, now that I have my 2 partial pressures, I can add them together, 2.9 plus 7.2, and they should sum up to the total, which is 10.1. Either way gives me the exact same answer. You can try it. So now you have 2 different tools in your toolbox. One way might be longer, one way might be shorter. We always want to do the way that saves the most time on the AP, but use what you're comfortable with. Okay. And notice, hey, more moles, more pressure, which makes sense. If I have more gases in here, there's going to be more collisions. We said think of pressure as the force per unit area, the number of collisions you have in there, because that would be what's exerting force on the walls of your container, and more pressure. Sometimes you might see these problems where you have bulbs connected to each other. And in this situation, there's kind of a little bit of a shortcut to do this. If you want to take a moment, pause the video, see if you can try what to do here. Otherwise, stay on the line. Some people might say hey, I have pressure and volume of the helium gas on this side, and I have a temperature. And same thing on this side, pressure, volume, and I have a temperature. And once I open this valve, these are going to mix together. The gas is going to expand to fill the whole container, because that's what happens when gases mix. And you might say, hey, the moles, though, are not changing. They're just spreading out on each side. So my moles are the same. So if I can calculate the moles on this side and the moles on that side with PV and RT, then I can add all the moles together. And then I can calculate the pressure. And I'll show you doing this out. It's kind of lengthy, but just showing you. If I find the moles of gas on the left side with the pressure, the volume, the temperature, here is my number of moles. And if I do the same thing on the right side, pressure, volume, temperature, to find the moles, and then I could say, hey, when I open the valve, these moles will mix together, so I can add them up, and I can find the pressure by plugging these added moles into Pivner, and then I would get, and now the volume would be 9 plus 3 would be 12 liters, then I could get 2.25. And that's a lot of work. And there's actually an easier way to do this. And it's really helpful to know this easier way, because sometimes they could give you a problem and it doesn't even have the temperature in it. And you might be like, well, how could I do this without the temperature? Well, the temperature is not changing. So to show you, what I can actually do is, hey, this is a change in conditions. I'm like, if I just consider the left side separately, it's starting at 2 atm and 9 liters. Once I open this valve, it's going to expand and the volume is going to change to 9 plus 3 is 12 liters. Now the moles are not going to change, right? They're just spreading out. So moles are constant. Temperature is not going to change. Temperature is constant. I can apply Boyle's law that P1V1 equals P2V2 because the temperature and the moles are constant. They would drop out of an equation. So if I do this, okay, and this is just looking at the left side, I'm going to consider each bulb separately. 2 atms, 9 liters. Okay, my second volume would be 12 liters, 9 plus 3, because when I open this gas is now contained in this entire thing. And if I solve for the pressure, notice it's no longer the same. So the helium gas that was once on this side, because it has a smaller volume, it had 2 atm. When I expand the volume to 12 liters, the pressure has dropped to 1.5 atmospheres, which makes sense. If the volume goes up, the pressure from the gas that was once on that side goes down. And I could do the same thing on this bulb. P1 V1 equals P2 V2. Here's my P1 and V1. My V2 would also be 12 because if I open this bulb, the gas expands. And my pressure again has gone down for the gas on this side. Now to get the total pressure after I've opened the valve, I can just add these two pressures together. This is the pressure of the molecules that were on this side. This is the pressure of the molecules that were on that side. The total pressure is the sum of the partial pressures, so I can do 2.25. Notice I get the exact same answer, but in this case, I thought my work was shorter and I didn't use the temperature. So if they don't give me a temperature, it's really not a problem as long as it's staying constant. I've seen problems where they have like 3 or 4 bulbs and you could still apply the same thing. Whenever there's a change in conditions, it's really helpful to use that equation with 1s and 2s. And just be careful when you do expand a volume, if you open a valve like this and expand the volume, the pressures don't stay the same anymore. Notice the pressure for each of these dropped. You can't just add these two pressures together and say 5 and call it a day. No, these are no longer true once you open the valve. There's one more partial pressure equation I want to derive for you really quick. So if we know that your total pressure is Pivnert, but plugging in total moles, we know your partial pressure is Pivnert, but plugging in your moles of your one component. You're solving the partial pressure for it. And I just put it as A for now, for component A. If we take these two equations, if we make a ratio of the partial pressure over the total pressure, then I would take this fraction and divide by that fraction. Now, if we have the same container, the volume is going to be the same. If it's a fixed rigid container, volume's not changing. If you hold your temperature constant, that's not changing. This is the same T. And if you have R, that's a constant. So these things would not be any different in either of these equations. The R, the T, or the V would not be any different. So we can actually cancel them out. And look at this ratio that we get. We get that the ratio of the partial pressure to total pressure is the same as the ratio of the moles of that one substance over the total. And that kind of makes sense, right? That even if you think of your ideal gas law, that pressure and moles are directly proportional, right? So that kind of makes sense that the partial pressure over total pressure is the mole parts over the mole holes. Now your equation sheet goes a little further, and they call this fraction XA, and they say XA is called mole fraction, the moles of the part over moles of the whole. And then they rearrange this equation. And notice it's dimensionless, meaning there's no units. Moles divided by moles is moles, and same on this side. Atmospheres, let's say divided by atmospheres moles divided by moles is nothing. Atmospheres divided by atmospheres is nothing. There's no units actually in here once you divide. So what they decided is, let's rearrange this and we'll write it this way. So this is the actual way it appears on your formula sheet, and this is what your formula sheet says. It says PA, and it tells you PA's partial pressure is the total pressure times the mole fraction, where the mole fraction is the moles of the part over moles of whole. If you like this equation better, that's totally fine. You will just not see it that way on your formula sheet. So when you see me solving problems, you're going to see me solving it this way. So this is just one more equation to know and to use. And why do you need this equation? Because you might have a problem that looks something like this. And if you want to pause the video to try it and then check your work, that might be a good idea. I'm just going to go straight to solving it, so check your work. If there are 60 moles of oxygen mixed with 20 moles of hydrogen, what's the partial pressure of each gas if the total pressure is 2.3? Look at it. They don't give you any temperature data. They don't give you any volume data. So you can't actually plug into Pivner to solve for anything. So this is where that other equation, they call it Dalton's law, or Dalton's equation as well, this is helpful in solving a problem like this, where they only give you mole and pressure amounts. And again, they might not give you moles, they could give you grams, you have to convert to moles, but they only give you amounts and pressures. They don't give you information about volumes and temperatures. So for this situation, I can still find the partial pressures because I have that total pressure, I have the moles of each, I can use this partial pressure equation. So for the oxygen, I'm doing 60, the part, over the whole moles. 60 plus 20 is 80. Don't do one part over the other part, it's part over whole. And then I'm multiplying this, which is the mole fraction, times the total pressure, 2.3. And I'm doing the same thing for H2, but this time I'm doing 20 over the total, part over whole, times 2.3. And I get my two partial pressures. And to get the total pressure, I could, if I wanted to, I could take moles of each, plug into, oh, wait a minute. No, I can't. I don't have Pivner. Oh, man. But what can I do? Oh, I have the partial pressure of each. To get the total, all I have to do is add them together. That's why knowing all these little rules are important, because sometimes there might be one that works for a problem and not another.